Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to get back into our little escapades with math and physics. So, honestly, basically I've been trying to figure out exactly how can I approach math and physics but in a united way, because yesterday you guys have saw that I was trying to do 2 math proofs yesterday, and they're very, I guess, for anyone that's an undergrad in mathematics, they probably would think it's very basic, but for me they were pretty tough because I couldn't break down the proof, and the proof itself was I guess it's something simple that an undergrad could do, but for me it was it felt like I didn't really think enough about how the definition should be explained in the proof, I think, and I think that's the thing that was most difficult for me. So for me, I began to think about what is my goals with math in general, and my goals with math are as follows: is know enough math to make it applicable to physical systems, and honestly I like physics because it helps you develop an intuition with math. So I thought maybe I have to actually go back to the try to reformulate how I think about the approach when it comes to actually preparing to study math and study physics in general, because I think the thing that intrigues me about math is its higher application with physics. So I think that's the main thing, and the thing of it is that if you really want to get into theoretical physics, and I'm not planning to for me, I'm trying to develop my own way to do it without, having the need to go for a PhD or anything like that. Or at least, look at a symbol and understand what it means. That's, one of my goals. Just basically look at the equations and understand what they're talking about. The more you're exposed to math, the more you begin to familiarize yourself with the symbols and stuff. In addition to, when you actually understand things like what a derivative is or what an integral is, not in the most rigorous way, but in a way that is, I guess, that makes sense to you, you begin to develop an intuition to it. So that's mainly the approach I'm trying to redo for myself, because usually when I do mathematical proofs, I usually separate it in the domains where it's this is math proofs and this is physics, or this is physical math and this is purely mathematical. So I think the point I'm making is that I'm trying to develop a strategy where I can unite the two, so it doesn't feel as if it's oh, this is only for mathematical proof writing, this is only for physical, this is only for physical application. And I think that's the thing that is important, is basically trying to discern the goal that we're trying to develop, or at least I am. You guys probably have different goals when it comes to learning mathematics, but mine is basically just learning the proper mathematical tools that I need to basically understand deep physical ideas. And I think that's the thing that intrigues me about math. I do love abstract math, don't get me wrong. I do think pure math is like, it can be beautiful in its own right, but at the same time, I think my more, like, the honest truth to myself is that I come to the realization that I really like math for its physical applications and not for the deepest purities of it. I can appreciate it like any person would, like once they know the underlying formulation or the imagery that they can develop in their mind, and they could sort of get it. Like, because for me, whenever you guys explain like mathematical concepts to me and I don't know what they are, either I will look them up, or you know, ChatGPT is like kind of like a friend for me, because it's like I would type a mathematical idea and I would be like, what does it mean? And then I would read some parts of the definition, and then I would try to develop an image in my head on explaining what that mathematical idea is. So and it also depends on your own curiosity about it too, because like if you have the curiosity to know it and you really want to put a little bit of effort to actually trying to make it easier for you to think about it, I think you will find a way to actually develop that. So that's usually how I think of it. And even though it might be it might misconstrued by interpretation, but at the same time it's something that helps you hold on to the image, or helps you hold on to the idea, and when you hold on to the idea you can develop it as you go. So like when because basically I'm just looking through different books right now when it comes to like explaining, I guess, like higher levels of math, but from a physics point of view, and I think that is very important. But I think since we are going to lean more into physics, I think I should do some physics problems, because I think it'll be better if I apply some physics knowledge, because I think the thing I like about physics is that, and math books do this too, but usually I think math books, they stop doing this when it comes to like higher level maths, because obviously you have to prove things and they don't really show you that many examples. They tend to have a streak with that, but with physics, I think, like, you know, at least university level physics, they have the ability to explain things in a little bit, I guess, a little bit of a noob approach, I should say. I think we should go into energy. I mean, I remember the equation for kinetic energy. So why don't we just practice some kinetic energy problems? And I think we're gonna have to get a figure here, because it's like figure 6.3. So, oh, here's a figure. Here's the figure, I think. So we'll just take that, and then we'll paste it right here. So that would be. Yeah, I know I mainly just put maths here, but like, luckily it's in the Origin of Maths playlist, so that's the playlist I put in whenever I want to do both physics and math in one stream. Excuse me. Okay, so I want to make sure that, so what they explain here is the equations for work. So far we're going over work, so this is a work-based problem, I think. And yeah, this is the distance here. So it's the dot product between the distance and the force, okay, but it can also be... So the thing of it is that since we have two equations here, I have to make sure when these equations are used, because sometimes when I'm given equations, I forget that there are certain conditions that these equations have to be used. one example is that if you're doing like regular kinematics, you're given the equation for like the final position, and there are times when you can simplify it, and there are times when you have to take the derivative of that function. And sometimes I forget when to apply the derivative and or when to integrate the function compared to like what is given, and then I don't have to do those things at all. So those are the things that I try to keep in mind. I may know the equations, but I don't know when to apply them correctly. So those are the things that I try to keep in mind when it comes to physics problems. Because we know work is a scalar, so we basically have to do it this way. Okay, so I think we can just like, is this problem? Okay, so I want to make sure there was nothing else involved. So okay, so the problem we got is Steve exerts his force with a magnitude of 210 newtons of force. So we'll just put a vector there because we know force is a vector, which is about 47 pounds. On a stalled car in figure 6.3, which we got here, as he pushes the distance, so we'll have a distance of 8 meters. The car also has a flat tire, so to make the car track straight, Steve must push at an angle of 30 degrees to the direction of motion. How much work does Steve do? Okay, so we have to put in how much work does Steve do? That's A. And for B, in a helpful mood, Steve pushes a second stalled car with a steady force of, okay, so in this one we have to remember that the force equation is, so we have to probably figure out the angle of this one before we apply it to anything. And the displacement of the car is 4 meters. Okay. So now the question is, how much work does Steve do? So both of them are just work-related problems. So we're gonna have to do the first one. Alright, so what we know about work. What we know about work is that we have two equations. We have force, the dot product between force and distance, but we also have the magnitude of force and the magnitude of distance, the cosine of phi, or yeah, maybe we should rewrite this as phi or phi. I don't remember how you pronounce that. If anyone in the chat wants to correct me, please correct me. So I think with this one we have the angle and everything like that, so we can actually do that. And I think the next one we can apply the dot product function, because I think that one is more convenient to do. So for this one, we can just basically plug it in our calculator because we have like everything. degrees. So the amount of work we get is 500.1. And work, I think, is in joules, because we have newtons and then tons. Yeah, I think that's joules. So I think it's this. And I think for B, we're just going to have to apply the dot product, which is times plus -4 newtons times which gives us 13 plus -4d. That's a lot. Hold on, maybe I think I have to change modes here. Yeah, I knew it. I was in radians. I should have been in degrees. So I gotta do these problems over. Because usually I'm so used to having my calculator in degrees, but I think there was one problem I had to do in radians. Okay, so I gotta change it to degree mode for the first part, so... And then times 18, and cosine 30 degrees. There we go. Actually, I have to check with the degrees to make sure that, okay, so is an angle of 30 degrees from the direction of motion. So I'm guessing it's, yeah, 30 degrees, so it's basically, so yeah, so we got 3,000. We'll just round it up to joules. Okay, so then he pushes a second car. Just want to double check here because the numbers look kind of... I want to double check here with this. Okay, so I didn't miss any negative signs. Yep, it's still 1800. So actually I want to calculate how much force that is, because he's applying 210 so, and then plus -40 squared. Okay, so basically the amount of force that he's applying to the second car is around like 164.9, so around like 165 newtons. So it's much less than the force that he's applying on his car. So I think that could be. Hopefully I applied that right, because I mean it's kind of obvious because you're given like in vector form, so I think it would be easier just to do the dot product version of it. So let's take a look. Yeah, so we have, okay, so yeah, that's around 1,000. Yep, we got those right. Cool. Yeah, I thought that was something funny when I was doing the numbers here, and I was like, oh wait, maybe it's in radian mode. Luckily I checked. Okay, so we can do the basic work problems, so that's good. I think with me, it's like when I do physics problems, I always remember the equations very well. It's just that depending on the problem, I have to know when to apply certain techniques, and I think that's the thing, because Sometimes when you like study the math of how it's supposed to work, or like how you think it should be set up, you get so used to it that you don't think of the actual physical system. And that's the thing that I try to be very wary of. So let's see, what are they going over in this one? Positive work, negative work, and zero work. Okay, so I think we can look at this graph here, because like I'm trying not to read a lot paragraphs because I know physics is a lot of reading. But mainly I read it because it's like it'll give me like I think physical intuition, because the thing about like physics, if you really love like I think like theoretical physics, you're so used to being wedded to the math, I think. But at the same time you also know you have to develop the physical intuition. That's why they have like that's why they make you do like lab work in physics. Because it is a legit science, so there has to be experimental lab work involved, and it also helps develop your intuition like physically rather than mathematically. And I think that's the reason why some mathematicians kind of like don't like physics because it's kind of limiting. Let's see. The direction of the force of the first component. Okay, so we have parallel force and orthogonal force. So obviously if the force goes in the opposite direction, the work is zero, because obviously like when you do the dot product of that, you know that the vectors are orthogonal to each other. Let's see, force F has the component in the direction of the displacement. Work is positive. The force has the component opposite to the direction of the displacement. So force is so work is negative. And the force of the component is perpendicular to the direction of the displacement, so there is no work done. Yeah, I think that's the reason why they tell you that even though gravity is a force, it doesn't apply any work, because it's because obviously like gravity is like working. I mean, like gravity is working in the vertical axis, and if you're going somewhere like, you know, in the x-axis, it doesn't affect it. Thus, no work is done if you're just standing still holding a box. Let's see, a body lifter does no work on barbells as long as he holds it in stationary. Yeah, because basically he's just lifting it up and down mainly. This weightlifter's hand doing negative work on the dumbbells, as the barbells does positive work on his hands. So this is the distance here. The barbells do positive work on the weightlifter's hands. The force of the barbell on the weightlifter's hands is the same the direction as the displacement. Okay. The weightlifter's hands do negative work on the barbells. The force of the weightlifter's hands on the barbells is opposite to the displacement. Okay, so this is positive because it's going with the displacement, because the displacement is also a vector. Okay, so we have another practice example we can try. And I think I'll probably skip around to try to do some electric problems, because I've been kind of backing out on electricity for a while, so I think maybe it's time to actually try to engage with it a little bit. Let's see, a farmer hitches a tractor to a shed loaded with firewood, pulls a distance. Oh, we have a figure. So let's see where we can find this figure here. Oh, okay, here it is. want to make sure I don't look at the answer while I'm doing this. That's the reason why I'm trying to be careful. I mean, you guys may see it, but I'm trying not to see it for myself. Hey, Van Foxman. How are you doing? What's the best part of your day so far, my friend? Okay, so we have a distance of 20 meters ground level. The total weight on the sled loaded is... Okay, so we have a force of 14 newtons. The tractor exerts a constant force. So wait, I should probably put this the force of the sled. And this is the force due to the tractor. 5,000 newtons at an angle of 30 degrees. Above the horizontal, okay. And we also have a force of friction. Oh boy, that's fun. That is 3,500 newtons of force. Okay, so we have friction involved, so this is going to be a little bit more complicated. So find the work done by each force acting on the sled and the total work done by all forces. Okay, so we have to figure out the force on the sled first. Work on the sled. Okay, so we know that we travel, so let's write down our equations. So work is force, the dot product between force, but it can also be the magnitude of force and distance cosine wow. There we go. That's what I want. Okay. And we also know that work comes in pairs. That's the... And we also have a free body diagram, which helps. So... Alright. So the work done by the tractor... So... Well, actually, we can just calculate everything. So we can just erase this top part here. Alright. So we actually have to calculate all the forces together, which is going to be fun. So let's see, the total load of the sleigh is 14. So that's the amount. Hey me, Machine Rex. What's the best part of your day so far, my friends? Okay. Yeah, once friction gets involved, that's what. And I'm trying to reread the second sentence. The total weight of the sleigh loaded is... So... That's gonna act... So let's think of the sled here for a second. Because the force on the sled, we're just gonna say it's 14,000 newtons in the J direction. Well, actually, we could probably put a negative there. And the force of the tractor exerts a constant force of 50 above the horizontal. Okay, so the force of the tractor, or at least the distance it's going, is around like 5,000 newtons with an angle of 36.9 degrees. Maybe I should just put this in parentheses here. And now we also got friction, which is basically acting against this, so I think for both systems, or at least like for the sled with the tractor, we also have to include friction with that. Force of friction, we will have newtons because if we did cosine of that, then yeah, because cosine would probably be like in the x coordinates. So I probably just put an I here. So I think we're gonna have to do, so I think what we have to do is that we have to take the total force of these two and then basically multiply it by the distance here. And I think that's what we can get. So I think we gotta put like an I here, because that's just the force of friction. So we're gonna have to add the tractor plus the force of friction, and then that will give us the force that we need, F. So do 5,000 times cosine of 36.9. You add that with negative 13500, which gives us a force of 498.4 newtons. Okay. So now we can take that amount of work that's done, that amount of force that's done, and I think we can put it in our our work equation. Because usually if it's vertical, it's not going to do anything. And I know that 180 degrees, if you do cosine on that, then basically that's a negative version of that number. So I think in this case, we multiply this by is it 20 meters? Yeah, 20 meters. Hopefully I get this right. Times the cosine of 2.9. That leaves us with a work of 7,971. Well, actually, we'll put 72 to round it up. Joules. And I think that's like everything involved. I think. that's the best way I can break it down. If I'm wrong, I'm wrong, but you know, you guys have seen me get answers wrong on this on these live streams before, so you know, it won't be anything new. And plus we learn something if we get it wrong. But yeah, when I think about it, because it's not doing any work in this direction, so we don't have to worry about this. The tractor is pulling this way, and we're not given the mass of the tractor, but I don't think that's relevant here. We know that the angle that the pull is done, that's the force, and then we know that the force of friction is in this direction, because I think like we don't have to calculate friction because it's already here. Because I know there's something involved with, like, you know, the mass of something, but at the same time I'm like, do we need to do that here? Well, not the mass, but basically the force of gravity on to get friction. Mainly like the weight of the object involved with friction, and I don't think that's gonna be an issue here, but it could be, but we'll see. Alright, so we'll just have to remember 7,972 joules. Okay, let's see if we did alright here. Let's see how it worked out. Looks like we were falling short. Yeah, I kind of had a feeling that I was getting it off because let's see what we got. I mean, we did this operation right, but I guess I didn't take into account like the force of the object, which I probably should have. I had a feeling that was gonna bite me in the butt. Okay. Alright, so what did we do wrong here? Let's see. That leaves the work on... So the work... So what is W? W, work done by the weight is 0, so the normal force is 0. Yeah, that I was aware of. So the tractor and the distance, that's the amount of work done here with just the tractor, and the work done by friction. Oh, okay. So... Oh, we did like a little bit of the second approach here. So, in the y-axis... you don't need the second equation to know that... Yeah, so that's what I was thinking. So... Let's see, work total. The sum of the forces. Oh, so they didn't put the cosine in this one. Maybe that was my flaw with it. I guess I should have done the dot product instead of just doing the angle. So if I were to do it the way they said to, and then we have the distance of 20. Yeah, that's pretty much like close. So I think what I did wrong was that I incorporated the angle, which I probably shouldn't have done. I should have done like the dot product version. Yeah, see, this is where it like, this is where it actually comes to like knowing where the math is applied and when it's not. So I think because we did the angle for the force of the tractor, it probably already incorporate that. So, and plus we were given like a new force. So the new force is basically a vector where it's like we don't have to worry about the y component. So yeah, I got like close when I redid the calculation. I got like around like this amount. So we were close. It's just that we were off because I added the angle where it shouldn't be. And I think it's when problems like that you have to actually become aware of like when to actually implement stuff. Because like I remember the equation, but I just didn't know where to apply it in the appropriate way. And I think that's when like you have to be aware of that stuff. And I think when it comes to that stuff, that it can feel discouraging when you get it wrong, because like I knew the equation, what did I do wrong? And then when you look what you did wrong, you're like, oh, that's why. So I'm guessing because they didn't do the cosine, because they were doing the dot product version of it. So it's like, yeah, right here, because it looks like they just did the distance here. So did they say why they didn't put the angle? We don't need the second equation. So it must be 0 anyway. Okay, the total work is therefore done. X component. Yeah, because they did the dot product version of it. And then the sum of those forces is like 500 somewhere. So maybe we can ask ChatGPT why they didn't put the angle. So let's see if we can copy this. I was actually looking up no. See, I hate it when it does that. I don't want the code, I just want the image. I don't want to have to like do the whole thing again. Yeah, I just want to ask ChatGPT why they didn't put the angle for the maybe I should also take a picture of the second part. Because sometimes I have an idea why I got it wrong, but I just want to make sure that that's the thing that I'm thinking of that means that it's wrong because of that way of thinking. When calculating the sum of the forces, cosine Usually these type of questions you need like tutors. That's why I'm kind of glad that like AI is actually kind of implementing sort of like tasks like this, but at the same time, like we can't over rely on it yet. So it's like they sometimes can give like the wrong and correct answer sometimes. But I think with basic operations, it should be able to handle it. Missing cosine is already accounted for. Here's what was happening. Okay, so my reasoning was right, because since it's already incorporated in all the forces that were calculated before, we don't no longer need to incorporate it now. Okay, so I guess that's a good mental note to think about. With friction. Okay, so we kind of like learned about that. So what it involves, basically doing more stuff. Know that the angle is applied once. That's something to keep in mind. Yeah, see guys, like I get it wrong so you don't have to. That's a good way of phrasing it. It's a good way of making myself feel better a little bit. Oh yeah, the work energy theorem. I think we can probably mess with this too. So the total work done is the amount of kinetic energy, the difference in kinetic energy. So we already know the definition. So the definition of kinetic energy. I think most of us that are studying physics are familiar with this. So I think that is that's something we can remember. Okay, so here's another problem we can do. All right, so let's take this. Let's copy that. Paste that there, and I think after we do this work theorem problem, work kinetic energy theorem, the work energy theorem, we can probably try to do some electricity-based problems, because I kind of like remember Coulomb's law and stuff, but the other stuff, like you know, the deeper intricacies of electromagnetism is still elusive to me. Like I don't remember the back of my hand like I remember like F equals ma. So figure 6.7, 6.10, 6.8, 6.7. Wait, hold on. Look at the slave figure. Our results from, suppose the sled's initial speed was, what is the speed of the sled after it moves? Okay, so I guess it works off the problem we were doing before. Okay. So suppose the sled's initial speed was 2 point, okay, so initial speed was 2 meters. What is the speed of the sled after it moves? So we'll just draw an arrow. 20 meters. Okay. So I'm guessing we're gonna have to figure out the acceleration of it. So in this case, I'm the same. My basic mechanics is much better than my electric magnetism. Yeah, because like with electricity and magnetism, like when I think back, I'm like, with mechanics I remember things like torque and stuff, but at the same time it's like I don't remember the equations by heart. But when it comes to electricity and magnetism, I'm like, wait, I like the only thing I remember from electricity and magnetism is like, you know, opposites attract, like charges repel, and Coulomb's law. But visualization wise, I can't remember, like, you know, like I can't draw pictures in my head. And I think that's the thing that's kind of like making me feel a little bit inadequate when it comes to electricity and magnetism. Like, my dad is he really likes to repair things, and he knows like things about electric motherboards and stuff, but he's mainly like has repairman knowledge. He doesn't really have like knowledge involving like the theoretical parts. So like it's just kind of ironic, actually, that like I'm actually going into the details of the stuff that he probably already knows, like for first-hand experience. Like, he can do basic algebra when it comes to like the circuits and stuff, but when it comes to like, you know, like I think the force of a magnetic field or electric field, I think like that's something that he probably would have to like pick up like a book to actually like read up on. But unfortunately he can't read English, so he can only like probably like look up, like, if he was curious enough, he would probably have to look up like a Thai YouTube channel to basically explain everything. If he needs to, he probably might catch up. He'd probably be like, oh yeah, I remember that. But unfortunately my dad's not an engineer. He probably would have made a good engineer if he went to university like in the United States, but my dad was just more content about just like, you know, starting a life, like just starting a life rather than just going to school. Okay, so I think we have to figure out the acceleration first. This should be fun. So we know that the mass of the force of the sled is 14,700 newtons, and we do know that the acceleration due to gravity is 9.18 second. And I think we just need to get the weight, because like this is technically the weight of it. We just need the mass. So actually, I don't want to confuse that with work, so we'll just put we'll just leave it the way it is. We'll just leave it like force. So the mass is equal to the force divided by gravity. Let's move that over there so you guys can see it. So, and divide that by, because I think we have to, so the mass is 1,000.5 kilograms. Although for me, sometimes I probably should work on the significant figures, because when it comes to the significant figures, sometimes I don't pay attention to it. I just write some numbers willy-nilly, which I probably shouldn't do. Because I think the epiphany I came to is that scientists, they're just great at estimating things. I don't know, I think like the reason why I came to that epiphany is because whenever I started doing physics problems, I would look and see if my calculations are in the ballpark of whatever it is they showed on the example. And if I get somewhat close to it, I'm like, okay, then my technique was fine. I don't know if that's the right attitude to look at it, because like I noticed that I think a lot of scientists, like, they're successful because they are good at making estimates and doing, like, obviously, like, if they know how to do the equation in their head and they have easy numbers, then they can make good estimates on it. And they probably know which data to filter out. I mean, that's my guess. That's my guess of why scientists are so sought after, because they're so good at doing, like, experiments all the time, that they have gain the experience of just being able to estimate things, like just by thinking it in their head based on their experience and their education. But of course I know that's probably not everything that makes a good scientist, but I think that's like probably some of the key features. Not all of them, just some of them. Just some of them are the key features. Okay, so now we have the mass. Now I think, and if it's initial, it gives us our initial velocity, so do we need to calculate the kinetic energy? That is the one thing that I'm curious about, because we're doing this based on the theorem here, but at the same time, like, I want to make sure that because if its initial velocity is basically this, then we know that once it travels like 20, so I think we're gonna have to use the kinematic equations of distance, because we know that the final distance is 20, so the final distance is 20 meters, and I think the kinematic equation we have to work with is, because we know that the initial is 0, so we don't have to put that there, so I think we need the initial velocity, time, and then plus a half as the acceleration time. Now we don't know the time, so I think what we can do is that we can get the final velocity. Yeah, because it says what speed this. Okay, so I think we don't need this equation actually. We don't need this. What we do need is that, so it would have to be the square root of the initial velocity plus 2 times the acceleration, and the difference in distance. So we do have delta x, which is 20 meters. Now we just have to figure out what the acceleration is in this system here. So so we got the mass here for unless we don't need this, because I'm thinking about the work value theorem, the work energy theorem, because it's the difference between kinetic energies. But then again, we don't know what the final velocity is, and we need the acceleration. But that's the only thing we're missing here. So I think it involves a little bit more work. Okay, so. Okay, so we know the force is this. Technically they're probably going to round it to 500, but we'll keep the number we have here because, so we know the mass and the amount of force, so now we need to know the acceleration it's going. Okay, so I think that would work because this is incorporating every single thing. So so we can basically take this force and then basically figure out the acceleration from that. So it's going to be same F equals ma. We're just going to put t for we're going to put just regular F equals ma, and then we're going to put the mass of the sled and the acceleration. So we already know what those are. So the acceleration due to this sled, so that would be 480 point, how much was that? 480.4 newtons over the mass of the which leads us to an acceleration of, I'll just have to type that in my calculator, 1498.5. So that gives us an acceleration of 133 meters per second squared. Okay, so we can plug all those numbers in to our equation right here. So that leaves us with, so it starts off with a velocity of 2.0 squared plus, don't worry, I remember to incorporate the square root on the square root above everything. So I have the square root of 2.0 squared plus 2 times 0.33 meters per second squared, and then times 20 meters. That leaves us with a velocity of 4.15 meters per second. So I'm guessing, like, if they did use 500 and stuff, they probably will get it close to, like, maybe like 4.5 to like 5 meters per second squared. I mean, that's the way I would probably do it, based on the information that we have. And I think that would be a correct assumption here. So let's take a look and see how they did the problem. So, okay, 4.15. Okay, so I think we did it right, because we're like practically like, so, oh, they used it a different way. Okay, yeah, I got a feeling they were going to incorporate kinetic energy into this. I just did it like a totally different way. Yeah, because like, oh yeah, so we did this part, that one we did. And then using the equations, yeah, so we did it using this equation. So let's see what they did with the other method they did, because I think that's also interesting to keep in mind. So, because I think the reason why we didn't do it that way is because we didn't have the final velocity. And the whole point of the problem was to get the final velocity. 3,000 joules. So, oh, okay, so you just have to remember the total work that's there, and then basically you, okay. So there's like multiple ways of doing it, because I forgot that we also calculated the work done before in the previous problem, but I'm not too disappointed about that. Like, I'm actually I kind of like my method, because it allowed me to think about kinematics as well. But it's also interesting that basically the work the work energy theorem basically allows us to do that. So it's like the total work done due to the difference of kinetic energy, which I think is pretty intriguing, actually. It's a pretty interesting theorem, actually, because it's like the amount of kinetic energy that is in a system is going to actually lead you to how much work you're doing, which I think it's a pretty interesting connection when you think about it. Okay, I did say we would probably try to do some electrical problems, because I feel like I haven't had enough experience with those. And plus I kind of go into mechanics like sometimes a little bit too much, and I kind of like back out and doing these. So let's see. Electric charge, Coulomb's law, electric field lines. Okay, yeah, definitely we'll cover these, because I do know Coulomb's law. It's just that doing this stuff afterwards, like, that's the stuff that I kind of miss out on. Because I think this is just a lot of text. Yeah, it's a lot of text. I'm just gonna read the stuff that is in yellow, so that way I can basically get a better understanding of where we're gonna go with this. Okay, 2 positive charges or 2 negative charges repel each other. A positive charge and a negative charge attract each other. Okay, that's something we remember from basic science class. The algebraic sum of all electric charges in any closed system is constant. Okay, so electric charge is conserved. Okay. So the magnitude of the charge of an electron or a proton is the natural unit of charge. Okay, so all right, Coulomb's law. Here we go. The magnitude of an electric force between 2 point charges is directly proportional to the product of the charges, inversely proportional to the square of the distance between them. Try saying that 3 times fast. Okay, so the thing we have to keep in mind are these values. And Coulomb's law here. Coulomb's law, force between 2 point charges. Okay. Yeah, the one thing about electric magnetism that I always forget is that there's a lot of constants involved. It's just kind of amazing how distance plays a part in both fields of gravity and electromagnetism, but at the same time they kind of work like it seems as though like it's just interesting like how weak it is like compared to okay, what do we got? Electric force versus the gravitational force. Oh yeah, I think I got this problem wrong because I was like doing it I wasn't sure how to go about it, so maybe we can, I'm not going to try to look at the solution because I kind of remembered how it was done, but I don't remember the exact value, so I want to see if I can remember how to organize it in my head. Okay, so we got an alpha particle, the nucleus of a helium atom has the mass of 6 point. Okay, so we can just write that down. 6.64 kilograms, and a charge plus 2 electron charges. Well, technically it's supposed to be protons because it's positive coulombs. Compare the magnitude of the electric repulsion between 2 alpha particles with the gravitational attraction between them. Okay, so they want us to use the force of Coulomb's law between these 2 charges compared to the force of gravity. I think we can just put a B there for the electric field, and G, so it's like G times the distance between them. Okay, so I think the way they did this was that you had to compare the strength of the charges. So I think you had to do it like this. Because I think the reason why I got confused with this problem once was because we didn't know what the distance was. And I think that was the thing that was kind of like eerie to me. But I remember looking at the solution and it was sort of like this. And basically if you do this like so, and then you have to do it like you have to flip it over, so the distances become irrelevant at this point because they immediately go away. Let me just erase this actually, because the G is supposed to be on the bottom, so it's G times the charges underneath, and then we are left with K G underneath between the charges. And basically you just cross the charges out and it's just K over G at that point. And like K, what is the value of K again? Oh, it's close to 9, so I think we'll just round it up to like 9 point, was it 9 newtons? So Newton meters coulomb. So we have newtons times meters over coulomb. Is it coulomb squared? Yeah, coulomb squared. Meters squared and coulomb squared. And I think for Newton, I think Newton's constant of gravity is I think it was 6 point. I think I'm gonna type it up in Google, or maybe I can look it up in the book. Mechanics. Applying Newton's laws. Yeah, Newton's laws of motion. It's gravitational law. If it's in this section. Applying Newton's laws, dynamical equilibrium, fundamental. Using the second law. Where is his gravitational? Okay, so that's. Where's his formula for like the strength of the gravitational force? Oh, maybe it's this one. Yep, here it is. 6 points. Okay, so I don't think we can properly round that. So we'll put like 6.7 times 10 to the negative 11th, right? Yeah, 10 to the negative 11th. Newtons meters squared, right? Yeah, Newton meters squared, kilograms squared. Okay, so yeah, so bring this down here. Okay, now the fun part. Just dividing these things. Then times 10 to the negative 11th. I mean, the difference between them is like humongous. 5.20. And if you do the units, then basically coulombs times kilograms. So that these two will cross out. And we're left with kilograms squared over coulombs squared. But I don't think the units are gonna. I think it's just gonna be like how much the difference is between the two. Coulomb's law. I think this is where it was. Yeah, we did round it. We did the same thing. Oh, okay. We forgot to include this part. Let's see, the mass is squared and oh, okay, yeah, that's what we forgot. We forgot to include that section. I thought the amount of charges would cancel each other out, but I guess not. Oh, because it's masses. This is charges. Oops. Oopsie. See, that's the thing, because I got so used to like people comparing these two formulas, I forgot that this is masses, not charges. See, guys, I make these mistakes so you don't have to. So I have to remember that it's not charges. This is masses. So this is mass 1 and mass 2. So mass 1, mass 2, mass 1, mass 2. I knew I was missing something. Mass 1, mass 2, but like usually it's those small details I always miss. So I think this part, this is where we got wrong here. So we'll just erase this part here. Oops. No, I didn't mean to erase that one. So in this part, and then we'll erase this part here. Okay, so basically it has to be like this. And the masses are practically the same, so they just changed it to the charges squared and squared. But yeah, I think that's basically it. And what did they get? 1.3. And there's like a lot of interesting questions about that, because like the difference is so high compared to like the force of gravity compared to the charges. So the thing of it is that like I think like one of the questions I typed in Google was like, does charge add to the mass? And apparently the answer is yes. Charge does add to mass in some form or capacity. It's just funny. It's just so interesting that the two theories, well, the two forces, like theoretically, they kind of like are very different from each other, like comparatively. But when you actually do the formulation, they almost look similar, because like they were so similar that I ended up mixing up masses with charges, which is pretty funny. But like doing the actual like division between the two, I'm like, wow, the forces are completely different from one another in some way. But one involves charge, which is kind of like a part of mass, but the other one is like mainly contributing mass itself, which is pretty interesting. I mean, charge, I don't know if there's like a relationship between charge and mass though. Maybe we can type that into ChatGPT and ask is there a relationship between charge and mass? There's a deep relationship between charge and mass, but it depends on the context. In physics, we study this relationship in classic electrodynamics, quantum field theory, particle physics, and even string theory. Let's break down step by step. Okay. Classical level. I don't think we have to read the rest of it. I mean, maybe up to relativistic electrodynamics, but I don't think we have to do the other two. Let's see here. In basic electromagnetism, charge and mass are independent properties, but their ratio determines motion under electric and magnetic fields. Okay, so that's something to keep in mind. So their ratio determines the motion under electric and magnetic fields. Okay. For a particle charge Q and mass M, Newton plus Leibniz force gives. So force. So this is the force equation because the derivative of velocity is acceleration. Is equal to the charge E plus the velocity, the cross product of the velocity times the magnetic. I mean, I think this is the electric field. I think that's no. This is magnetic. Oops. So E is electric field and B is magnetic. That's my bad. When I was writing the formulation here, it should have been E for electric. Erase that. So put E like that, and E like so. Okay, there we go. Okay. So basically, it's E plus the velocity cross product of the electric field, the magnetic field. Oh, okay. So the acceleration depends on charge over the mass. Oh, okay. As it goes. Interesting. Okay, so we have to know what the electric field is. So we have to know what the electric and the magnetic field. But if you know this product here, then that means you might be able to determine the electric field by just knowing the charge, the mass, and this cross product here. Let's say the electron charge over mass, and the proton is okay. That is why electrons spiral differently than protons in the magnetic field. But here, mass and charge are not fundamentally linked. They're just two numbers. Okay. I mean, like, they do have a relationship, though, which I think is pretty cool. Okay, relativistic electrodynamics. Mass, energy, mass, and fields. Okay, Einstein's equations. Okay. E squared equals PC squared plus... So I'm guessing P is the momentum in this case. And M naught is supposed to be the original mass. Says a rest mass energy and the field energy are connected. Electric fields store energy, and its energy, and this energy has the effective mass of E equals mc squared. For example, a charged capacitor has more mass when charged than uncharged. Energy stored in the electric field contributes to gravitational mass. Wait, energy stored in the electric field contributes to gravitational mass. Okay. So while the particle's intrinsic mass isn't directly caused by its charge, the energy of the electromagnetic field affects the total mass energy of the system. Okay. So it's like they're saying that charge and mass, there is a relationship between them, but it's not extremely binding. It's not really like binding, as it were. So in other words, it's like they're trying to say that electricity and gravity, or electromagnetism and gravity, is sort of like they communicate with each other, but they don't really link up with one another in some way, some shape or form. At least that's what I'm getting from this, which is pretty interesting. Okay, so I think we can move on to other things here. The superposition of forces. More important, let's see. Coulomb's law, as we have stated, it describes only the interaction of two-point charges. Experiments show that when two charges exert force simultaneously on a third charge, the total force acting on that charge is the vector sum of the forces that the two charges would exert individually. So two charges exert forces simultaneously on the third charge, the total force acting on that charge is the vector sum of the force that the two charges would exert individually. So if it says vector sum, so I'm guessing you add the forces together. That's what it means by vector sum, I'm thinking. Okay, so two charges. Okay, so I think we can copy this. Paste it here. Alright, I'll be right back, guys. Just give me 1 second. Alright guys, I'm back. Sorry to keep you guys waiting. Anyway, before I carry on, if you like study streams, if you like math and physics, and you basically love the content that I'm putting out there, you know, consider dropping a follow if you're watching this on Twitch. If you are watching this on YouTube Live, you know, consider hitting the sub button. And if you're watching this after the live stream airs on YouTube, you know, like even if the live stream is up, you can hit the like button, and you can also leave a comment down below. The links in the description, the links for the Discord as well as my Twitch channel will be in the description down below, so you know, you can check those out. Like for anyone on Twitch, you can basically type in !Discord and it will lead you to our Discord server in the chat. So that's basically something I wanted to get out of the way before I forget, because I want to make sure that I say that so that we can continue on learning more math and physics as we carry on. So anyway, let us continue. Okay, so what we got two charges. We're gonna have to convert because these are nanocoulombs. So nanocoulombs, 75 coulombs. And the distance is 3 point. Oh, and we have a figure to so figure 21 and 12. 21, 12, where is that? Where are you? 21, 6, 21, 9. Oh, here. Okay. find the magnitude and direction of the electric force A that charge 1 exerts on charge 2 and B from charge 2 to... Okay, so I think now we're gonna have to convert. Because it's nanocoulombs, and I think it has to be coulombs for, like... so is a nano smaller than a milli? So let's see. Nano coulombs. Nanocoulombs to coulombs. I think we'll do the conversion here. So 25, 2.5 to the -8. So 2.5 times 10 to the -8 coulombs. I'm guessing -7 point. And I think it's going to give us the same type of answer. It's going to be like... Oh. Yeah, so -8 coulombs. Okay, so we know the formula is force is equal to K. The charge is, and oops, not K, R squared. So find the magnitude and direction of the electric force. Okay, so I gotta think here, because finding the magnitude, I think it's gonna be not too much of an issue. It's just finding the direction. But then again, they're going like we're thinking that the angle is not gonna be that much of an issue because they're going straight, I think. Hey, Goofy. What's the best part of your day so far, my friend? Yeah, mainly it's electricity. We're kind of going into Coulomb's law. Free time usually. Right. I think tomorrow we're gonna actually try to do more electromagnetism problems, or at least gain some more knowledge on electromagnetism, because I feel like with electromagnetism I've been slacking with it, because I only remember things like Coulomb's law and you know, like charges repel when like different charges attract one another. I mean, opposites attract, and like charges basically repel each other. Those are the things that I would remember. Okay, so free body diagram. So obviously they will be attracted to one another because one is negative and one is positive. So I think we can just use the regular distance, I think. It's just that since it involves two charges, we're gonna get the same answer, but at the same time it's like, I think one is going to be has a slightly difference here, because it says find the magnitude and direction of the electric force. Okay, so I think the negative is going to be I think the negative is just going to go towards the positive. I mean, they're both going to be attracted to each other, but I feel as if, like, I think they're going to be equal. They're probably going to be equally attracted to each other. I'm just wondering, like, how I don't think the answer is going to be different, but for some reason I feel like it might be slightly, like, a little bit varied from one another. Like, maybe, like, a minuscule amount, but... Okay. So, force from 1 on to 2. And I think K, we have to write K because I don't want to keep trying to remember that. So I think it's like 10 to the and coulombs squared. Let me see. I think it's like 9 to the 10, 11, right? Oh no, it's 10 to the 9, okay. Maybe it's gravity that's like minus 11. Maybe that's why I remember it that way. Right? Is that right? Yeah, so going back down here, right here, yeah. Alright, so... I mean, I think like one of the forces has to be negative, so that way you can basically get. So it's probably gonna be like, you know, because the force of the negative one is gonna go in the opposite direction. So we're gonna have to do the one with the first charge, which is positive, I think. So, the force of Q1. Now, so 2.5 times coulombs, and then times negative 7.5 times 10 to the negative 8 coulombs, and divide that, and then times so times 10 to the negative newtons. Oh, that's in centimeters. Oops. So we had to convert this. So 3 over 100. So that's. So I should have. Meters. So this one is not correct. So. 0.03 to the squared. So the force is negative 0.02 newtons. So I think like for the second charge, I think it'll be the positive version of that, because what force does charge 1 exert on charge 2, and what force does the gravitational force are negligible? Now the thing of it is that something in my head is telling me that when it comes to these two charges, I feel like determining the chart, like the way that direction impacts the other, we have to like get rid of the charge. But I don't know, I'm probably just making stuff in my head. Like I'm kind of psyching myself out, that's what I'm saying. Because I think for this one, it's not going to be negative, because it's going in the opposite direction. So we're thinking of like, you know, negative times a negative equals a positive, because it's basically based on the perspectives of both the forces. And it doesn't involve their masses, it just involves the charges between them. Now the thing of it is that like if it's based on just one charge, then if I'm thinking about it, like, because the way my brain is thinking about it is like I'm thinking about the force like on charge 1, it would probably be like something like this. I don't know if this is the right way of thinking, but it could be, but it could, but something tells me it might not be, but I'm just thinking about it. And then there's charge 2 over, well, K is still there, so K is here. And I'm thinking it's like basically on the perspective of both of them. So if that were the case, I want to see what the difference is. So I'm just gonna play with the numbers so I can create a better understanding of what is it that is needed in this. So let's do the first one. So this would be negative 7.5 times 10 to the negative 8. And then you divide that by so according to this, so if we do the other one times 9, and then the force difference is like, I mean, kind of like, wow. I mean, just between just those two things, but I'm like wondering if I'm thinking about this right. Because we got the magnitude, but like, how would you get the direction? because usually when I think of the direction, I'm thinking about because they're opposite charges, so they will be drawn closer to each other. Let's see how they solved it, actually. Okay. Alright, so they solved it the way we originally did it. Charges have the opposite sign, so the force is attracted to the left and attracted to the right. So yeah, it was the way I was thinking. Okay, so I was doubting myself with this, so this one is completely wrong. So yeah, sometimes when it comes to like doing problems, I sometimes psych myself out because I think, oh, there's some unknown thing that I'm not thinking about. You know, like those sneaky things that just like pop up and you're like, oh wait, yeah, that's right, I forgot about that part. I worry about that because sometimes when I feel like I know something, I'm like, maybe I'm being overconfident and I have to re-examine myself. But at least I was on the money with this, so that's good to know. Okay, so what about this one? Okay, vector addition on electric force on line. Okay, so let's see what this one is about. And I think like tomorrow we're gonna probably do more of these problems, just so we can get our feet wet with just electricity and magnetism. Okay, 2-point charges are located on the x-axis of a coordinate system. So, point, then that would be 1 point negative coulombs, and then point 2, that would be nanocoulombs. I want to convert these right away so I don't have to worry about them later. And x is plus centimeters, so that would convert to I think like 0.2 over 100. Yeah, so 0.02 meters. Okay, and oh, so this one is point charge here, and then the position here is positive 4.1 centimeters, which is 0.04 meters. Okay, so the question is, what is the total force exerted by charge 1 and charge 2 on charge 3? Okay, so we have a third charge here, so I think we have to add the charges together. Which is 5.10 to the negative 8 coulombs. And its distance is 0 meters. Okay, now, since we have two charges that are working, because I think in the book they said something about superposition here. Okay, so I think this is where superposition is gonna be involved here. So experiment shows that two charges exert forces simultaneously on the third charge. The total force acting on that charge is the vector sum of the forces that the two charges exert individually. Okay, so it's the vector sum of the two forces exerting individually. By using this principle, we can apply Coulomb's law to any collection of charges. Two of the examples at the end of the session. Okay. Strictly speaking, Coulomb's law, as we stated, it should be used only for point charges in a vacuum. If matter is present in the space between the charges, the net force acting on each charge is altered because charges are induced in the molecules of the intervening material. We will describe this effect later as a practical matter, though we can use Coulomb's law unaltered for point charges in the air at normal atmospheric pressure. The presence of air changes the electric force from its vacuum value by only about 1 part in 2,000. Okay, so it doesn't alter it that much. Okay. Now, it says like we're with forces individually, right? The total force acting on the charge is the vector sum of the forces that the two charges exert individually. So I'm guessing you're supposed to add the total amount, like add the force that you get from the two particles, and then you basically take the So I'm guessing what happens is that you basically take the mass of the first particle with the third particle and multiply that together to get the distance. So what is the total exerted on? So I'm thinking you're gonna have to do the distances with these all individually. So I think the force is going to be the total, at least. It's going to be K to K1 to K3. Q1 to Q3 over the distance between the two, plus the charge from Q2 to Q3. And now the question is that I think because the charges are working together, it probably should be like, probably have to count Q1 to Q2. I think that's how it's gonna work, because it says individually, so I'm thinking we're gonna have to do it part by part, because there's 3 particles in this whole thing, so I think you're gonna have to do it particle by particle. So I think do 9 times 10 to the 9th. And I think what we can do is that we're gonna do like the fraction approach, where it's it's going to be a long calculation. I think we'll probably just write it one by one, like each term by term. And then divide that by, so from from 3 to 1, so we have it at 0, and 1 is going to be here. So if you do the difference between the two, so that's... So we got... And then from 9.10, then we have, oh, almost forgot, that's a negative 1. So that's negative 8. Then times 5.0. Divided by, so the distance we have 4, so yeah, it's just I'm just calculating them individually because I feel like I'm going to make a mistake if I do it all at once. Like especially typing it all in the calculator. And then the distance between the two is... So I want to do like the second term again because I want to make sure that that's correct, because I tried to do so charge 2 is times and divide that by okay, so it looks like that is correct. Alright, now the hard part, adding all these together. And I think we'll end stream with that. Now, I don't know if we have to add like this part, that charge, but I'm just gonna include it. And then I'll probably do the result involving just these two. I think that will be something we can check. Because I want to make sure that I'm thinking correctly about these things. Because I know it's only for like the third particle, so. So either if it's these first two terms, it would be this one. If it's all three of these, it would be this. So let's take a look. So 28 micronewtons. So if it's micronewtons, I think. So I think it's this one. So I think I was right. So we don't really need this term. So we just needed these two. Okay, so that's a good thing to know. I think like what I was thinking about was probably like the whole majority of the system. So I just want to make sure that the units are right. Micronewtons. Oh, thank you for the raid, Academy. We're just doing like physics problems right now. Okay, so yeah, that would be it. Okay. But if you got on Twitch, if you guys are not, how was your stream actually, Academy? If you guys are not familiar with Academy, another awesome math streamer, more advanced stuff than me. So if you want to check out Academy stuff, aka the Academy of Useless Ideas, please be sure to check out Academy's awesome content. So yeah, there we go. But how was your stream, Academy? What were you guys studying over there? But welcome, Raiders. Welcome. I am Peter, aka MathSpellBook. If you like physics and mathematics, but like to do it, I guess, from the basic approach, you know, like, you know, you can just come in, relax, while we finish up stream, actually, because this was supposed to be my last problem, but we're learning a little bit about Coulomb's law and electromagnetism, because I am so behind when it comes to electromagnetism. So hopefully you guys can sit back, relax, enjoy yourselves for the last part of stream. But hopefully your stream went very well, Academy. And thank you for the raid. Thank you for the raid. Okay, I think that will be it for today, guys. Like, sorry to like get the raid and like do the problem and run, but it is that time. We will be back tomorrow, and I think we'll be doing more of these electric problems. Maybe we'll continue on with like the rest of this chapter, and I think maybe we'll try to get our feet wet with the other stuff, because the electromagnetism chapter is, or section I should say, is pretty long. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 chapters in that, so that's gonna be quite a doozy to run through. So I think we're gonna probably like explore electromagnetism a bit, because my physical intuition on electromagnetism is not very strong as it is with mechanics. Now, of course, mechanics I'm still kind of weak at too, so I feel like we're gonna probably just go through these, but at our own pace. And what we got left? We got optics, and then we got modern physics, but I think we probably have to go back to like maybe thermodynamics. Yeah, thermodynamics and waves. I think that's gonna also be a fun thing to do. Okay, guys, thank you for joining me today. Like I said, if you're just joining in and you like math, physics, or like, you know, need a study stream to keep yourself productive in front of your computer, you know, if you're on Twitch, hit the follow, like, drop a follow if you can, and if you want to. If you're watching this on YouTube Live, be sure to hit the sub button and, you know, leave a like on the stream. Or if you're watching this after the live stream airs, you know, leave a comment down below. And all the links will be in the description down below on our Discord server, in addition to my video game channel. And on Twitch, I will put that in the chat for you guys. So this is our Discord server, and this is my video game channel on Twitch. So you guys will have access to that as well. Once again, Academy, thank you for the raid. And yeah, so I think that will be it for today, guys. Tomorrow we'll probably just get back into electromagnetism and just, you know, get back into the material. So thank you for joining me today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. So take care, guys. Bye-bye.